introduce the second speaker today, who's Professor Jorge Lira from the Federal University of Ceará, Brazil. And the title of his talk is Conformal Killing Graphs with Prescribed Curvature.
Good morning. I'd like to thank the organizers for inviting me to this nice conference, and my congratulations to Marcos. And after he told us about the recent interest of Marcos in elliptic, I will describe what Marcos found in this new way of research in collaboration with me and other authors as Jaime Ripoll and Luis Alias. Then let me recall the classical results of James Serving about graphs. The first one, it's modeled in the Euclidean space, and you think the Euclidean space as a product space with fiber R, and given a domain in the second factor Rn, you define a function z in this domain, and then the graph of this function, this regular function, is the hypersurface squared by 2. So, of course, this vertical field is killing, generate translations, and this hypersurface, this graph, is prescribing curvature h and boundary given by phi in a function, if and only if z solves this equation, this quasi-linear elliptic equation. And you may convert this geometric problem in some analytical problem. In 3, gamma is the boundary of the domain. I'll keep this notation further. And h gamma is the mean curvature of gamma as submanifold of this Rn, this distribution of planes in Euclidean space. Well, the result of Serving is that one, if you consider mean convex domains, you have Euclidean graphs. If the mean curvature of this graph does not exceed this n minus 1 n up, sorry. Okay. If this value for h is not bigger than this fraction of the mean curvature of the domain. This is an existence and uniqueness result, and these two classical papers present the result first for minimal Euclidean graphs and then for general prescribed curvature. Modification of this result concerns radiographs. This time you see Rn plus 1 as foliated by concentric spheres, and then you consider the domain, this time at one of these spheres, the domain omega. And in terms of the radial coordinates t and the angular coordinate x, the graph is again given by this expression. And this time, of course, delta t is a conformal killing vector field, generating dilations. In terms of these coordinates, the metric, the Euclidean metric is that one, and the result of Serving is a kind of modification of the result for Euclidean graphs, with the only difference that the mean curvature is penalized by some function which is related to the boundary data. Some comments in these results by Serving. First one is that this quantity, h gamma times this number, is the mean curvature of the cylinder over the domain in both cases. The second one is that these results may be refined for continuous data. And both results are sharp in the sense that if you invert the sense of the inequality, you may produce boundary data which gives some non-solvable Dirichlet problems. Well, and then you may consider, you may put these results in a common framework, which is made described by this construction. You give a manifold M bar, a Riemannian manifold, endowed with a conformal killing vector field, and then you consider the orthogonal distribution determined by this field. We have y, a distribution y pep, inside some remaining ambient. Sometimes you consider the case when this distribution is integrable, sometimes not. And in terms of this killing vector field, or conformal killing vector field, the killing conformal equation is that one that says that y generates by conformal transformation. This is the infinitesimal version of this. And the same equation right in terms of connection is that one, 8. And you may consider the flow phi generated by y, the line flows which take a point of some integral leaf. You may integrate this distribution, for example, consider some integral leaf, and then define phi tx as the feature of this point of the leaf by the flow of y. In the case of radial graphs, of course, you just consider the radial vector field, and then the flow is just t times x. In the case of Euclidean graphs I described before, you have just the translation along vertical lines. Then, in this case, M is the sphere, and in this case, M is the plane Rn, the hyperplane. So this scenario includes both frameworks and on several works before. So phi is the flow generated by y, and M is the integral leaf I alluded before. In some cases, you refine this construction, considering that M bar is a remaining summation over M. And the vertical fibering of this summation are just the flow lines of I. This is other possible scenario for considering graphs. Well, the graph may be, the flow, may be defined for the entire line, but you may consider also incomplete vector fields. And just a fixed notation, lambda in the last line is the conformal factor generated by y at each time t. And joining the notations, lambda t over lambda is just the term which appears in the conformal killing equation. And both of these factors measure, in some sense, the mean curvature of the leaves of the distribution. Okay? Just looking for at the conformal killing equation, you may see that in the integrable case, this case, when the distribution is integrable, these leaves are total umbilical. And the mean curvature of the leaves is constant if you consider that y is closed. That is, that the dual formed y is closed. Well, considering all this notation and using the flow, fix the domain at the leaf, you may consider a graph by evolving this domain by some function z, and then you form here another hypersurface, which is the graph, the conformal killing graph of z with respect to this vector field. In terms of the flow phi, this is the expression. And then again, you reduce the problem to a Dirichlet problem for obtaining a hypersurface which is graph with boundary data and prescribed mean curvature. And using this formulation, the task is to produce a priori estimates in this general framework. For producing these estimates, you use the killing cylinders generated by the flow through the points of the domain. If you consider gamma here, the boundary of the domain, you have a hypersurface here, which you call killing cylinder determined by gamma. These killing cylinders provide some barriers to estimating height and gradient of the function z. Well, this is of course, the expression of k, just the flow acting on the points of the boundary of the domain. And then you may consider some examples of this. You may have, in general, in the case of integrable leaves and a killing vector field, not conformal, but killing. You have the case of static matrix which do not depend on t. This general example, which is locally presented by this equation, where the coefficients of the metric do not depend on t. This general example includes, for instance, a constant curvature matrix by describing this matrix in these terms, when R is polar coordinate in the leaf, and these functions ρ and k are given by the generalized cosine and sine functions. And other case is that remnant products in the case of a killing vector field which is parallel, and warped products are included in this kind of metric. When you consider this function, this field k delta t as a conformal killing vector field, and again space forms are examples modeled by this warped metric. So space forms, product space, and static matrices are examples of this kind of manifold. And in terms of these examples, you may think about some notions of graphs. First of these ones is the radial graphs, considered by Serrin and by Robert Finn and later by Rafael Lopes. There are existence results for radial graphs in Euclidean space, for normal graphs in hyperbolic space, and this time in hyperbolic space you may fix several possibilities of defining graphs. This, considered by Monteiro and Lopes, consider M as a Hor sphere in the hyperbolic space, in the half-space model. And then you consider the flow generated by these vertical geodesics. This is an example of this setup. And the existence result concerning this model was obtained by Lopes and Montiel. And also by a result by Nellier-Spruck, when they consider the case when the boundary data approach asymptotic boundary data at the infinite boundary of the hyperbolic space. Spruck also considered the same kind of problem, but for Gauss-Kronecker curvature. And you also mentioned other possibility of constructing graphs in hyperbolic space. This time taking totally geodesic plane, and then geodesics over some domain in this plane, and the graph we construct like this. This was considered by Nietzsche, and in both examples you have always umbilical distribution and fibers of this Killing vector field or conformal Killing vector field. The possibility is to consider graphs over geodesic spheres and over horospheres, but this time, or hyperplanes, but this time foliated by horocycles. This kind of graph was considered by Barbosa and Earp and by Earp and Gill. And other possibility is to consider closed graphs with no boundary condition. This time you have works by Barbosa, myself and Vladimir Joliker, by Yan Li and Vladimir Joliker, also comprising the case of high-order elementary symmetric functions of the principal curvatures of the graph, not only the mean curvature. Another approach to this kind of graphs was due to Klaus-Gerhardt using parabolic methods. Some comments about this kind of result. Of course, the main tool for deal with this problem is the continuity method. And it's often this formulation concerns creating graphs with a boundary, the trivial boundary, that is graphs which has the same boundary of the domain. And in this case, you have this Dirichlet condition, and age generally is taken as a constant. In general, these existence results I mentioned before treat this particular case. And this occurs because the barrier which is used to produce the estimates is typically spherical caps or umbilical surface, which are given by rotationally symmetric reduction. So you may reduce the PD for some ODE and solve the problem and use these solutions as barriers. And this will require that the mean curvature does not exceed the mean curvature of the boundary. And other maybe drawback in this construction is that the initial graph is sometimes given by the domain itself, not a minimal graph. Okay. And the estimates for producing these graphs usually combine these two functions, the height function, restrict to the graph, and the angle function theta, because there are some magic formula involving these functions, this one and that one. And if you combine these two formula, for example, if you take this combination age, which is the mean curvature, which is constant, the capital H is the mean curvature, the age is the height function, and theta is the angle. If you combine them, you produce a superharmonic function, at least in the case when the ridge curvature is greater than 0. And if you choose the orientation of the graph upwards, in the direction of the vector field, you have a non-positive mean curvature. And if you consider trivial boundary, you have age along the boundary equal to 0. This suffices to show that theta attains minimum at the boundary. And if you calculate theta, theta is essentially something like this. Then minimizing theta is equivalent to obtains maximum for the gradient. And then this kind of idea was successful to deal with these particular problems you mentioned, because it gives naturally C1 estimates for the problem. And generalizing this approach, the first results we try to extend these results with relative to space forms to other ambients were due to Marcos Dajczer in these works with Ripoll and Elias, when they consider the case of warped products in general, not on the space forms. And in spite of these first efforts, it remains some technical difficulties because they use essentially some adaptations of this construction I depicted earlier. And trying to solve these difficulties and to obtain more extensive results, less restrictive results, you turn back to the Serving's approach to the problem, using analytical barriers instead of these geometrical ones. And the first paper in this direction is that one. When you treat the case when y is a Killing vector field and the distribution is integrable, this time you use the Killing cylinders as barriers instead of this spherical caps or something like this. And the techniques were strongly inspired by the works of Tribex and Vai and Caffarelli and Berger-Spruck, because they use analytical barriers to solve the problem, in the case of closed graphs, in fact. A more general case is that of the submessions when the distribution is not integrable, but M is a remnant summation over other manifold. And in this case, the summation is pi, and the fiber is vertical. The flow line is vertical. In this case, this is the result. You have some control in the Ricci curvature in order to produce barriers, and you attain the same condition as the Serving's paper. That is, the mean curvature of the graph is less than or equal to the mean curvature of the cylinder over the domain, or the boundary of the domain. In this case, you have existence for any prescribed function satisfying that hypothesis, and for any prescribed boundary data. And some examples of this general result are the Heisenberg space, treated before by Alias, Dajczer, and Rosenberg. In this case, you consider Heisenberg space as submessions over the Euclidean space. BG spheres may be modeled by this, of course, and you may think about the graphs with prescribed mean curvature in these BG spheres. And an interesting case is a partial case is the liquidal graphs in Euclidean space. This picture right there, this kind of heliquidal moving, discrete motion in Euclidean space generates a notion of graph. And you have some partial result using essentially the general case. And as I said, besides using the Caffarelli and Berger-Spruck techniques, you also use in this paper some technique by Coreva. In that paper by Coreva, he combines two forms of linearizing the mean curvature equation. The first one by normal perturbations, and here appears naturally the Jacob equation, which is the approach I mentioned before. And the other perturbation of this graph is by graphical perturbations, and making expansions, Taylor expansions, in terms of normal perturbation and the graphical perturbations of the initial graph. Coreva was able to obtain interior C1 estimates for graphs in Euclidean space. You adapt these techniques, combined with the techniques by Tribex, Caffarelli, and so on, in order to obtain the C1 estimates in this very general setting of Killing graphs in a submetion. Well, the other step in this progression is to consider the case of conformal Killing graphs. In this case, the first result is about conformal Killing graphs, but with integrable distribution. In this case, the metric is locally put in this form. When dx is the metric, the remnant metric on the leaf, and the whole is a warping function, and lambda is a conformal factor, so combining this warped metric, and the conformal deformation of it, you have the more general possible scenario in case of integrable distributions. Here, rho squared is the squared norm of the vector field y. And you may think about this metric as a double warped metric if you make a simple change of variables. The equation turns out to be this one. You have the classical part, but this perturbation generated by the fact that the fibers of the flow have are no geodesic lines, and to the fact that the action of the flow is by conformal transformations. This generates this second term, and then you have the prescribed curvature H perturbed by the conformal factor lambda. This is an equation modeled on M, on the leaf M. And the condition for applying the maximum principle in order to have an invertible linearization of this equation is to consider these two equations. If you think that H, for example, does not depend on T, the first condition says that the leaves, the integral leaves, are mean-convex. If you consider the mean curvature of the leaves with respect to this inwards orientation, essentially the mean curvature of the leaves is given by this function. So you are assuming that these leaves are mean-convex. And the second condition essentially says that the mean curvature of these leaves increase when the radius decrease. Okay? These are sufficient conditions for having maximum principle for this equation. Okay, and then in the case of H not dependent on T, as I said before, a lambda T greater than 0 says that the mean curvature is greater than 0. And the second condition, as I said, measures this rate of the mean curvature of the leaves. In this case, you have this result. You always have a control in the ridge tensor, which is stated in more precise form this time. And the hypothesis about lambda. And then the condition about H is that H this time is not is less than the infimum of the mean curvature of the Killing cylinder. This time the Killing cylinder is maybe more close to a kind of Killing cone, in fact. You may have conformal deformations, and this relationship between the both curvatures, H and HQ, provide existence result for general boundary data. And this is the most general result we obtained. And some particular interesting cases are that involving closed conformal Killing fields, which comprise the case of space forms, for example. And this time the condition on the ridge is reduced to a condition on the ridge of the leaves, not the ambient ridge. And in the case of a Killing vector field, the relationship between both curvatures is given by this inequality, not a strict inequality this time. And I will give an idea of the proof of this result. First thing to consider is the geometry of these Killing cylinders. And for this, you use a Riccati equation to measure how the mean curvature of the cylinders increase or behaves in general when you deform the cylinders in the direction of the inward normal. How the mean curvature of the cylinders evolve, and this requires to use, of course, Riccati equation. And this is the step of the proof when you use the condition on ridge tensor. This ridge radial is essentially the ridge tensor measured along these lines, these geodesic lines departing from gamma. And you are restricted to a domain, a proper domain of omega, 3 or 4 points of gamma. Essentially, it's the largest open domain when the distance function from the boundary is regular. The possibility of having this domain is given by this recent article by Lee and Nirenberg. Use the existence of this domain and use this a focal distance in order to calculate the evolution of the HQ epsilon curvature of the cylinder. So what permits to calculate this rate of growing of the mean curvature is this relation, which is, as I said, is obtained by Riccati's equation. And using this relation, you may see that the mean curvature of the cylinder increases when I decrease the radius, when I walk in the inward direction. The second step is to perturb the original problem, considering this family of Dirichlet problems indexed by tau. Tau equals to 1 is the original problem, of course, and then you use continuity method to study this family of problems. And as in the classical textbooks, you may see that the technique is just to assuring that this set of instants when the problem is solved, this set I is not empty, because by construction this problem may be solved trivially by the z equals to 0 at time t equals to 0. The openness of this set is given by the maximum principle, essentially. This is the reason of considering this restriction on the ambient geometry in order to have a comparison principle and the invertibility of the linearized equation. And the closeness of this set I is given by C2 alpha a priori estimates. You say that the Schauder theory assures that it suffices to produce C1 estimates, and then the machinery works by itself. So C1 estimates suffice. And these C1 estimates are obtained by using analytical barriers. This first one, phi, is just consider the boundary data, the infimum of the boundary data, and adding some function designed by hand. You produce high estimates using this. In fact, this is a sub-solution, but in the viscosity sense, it's a continuous sub-solution. And the gradient barriers at the boundary, at least, are given by this other function, f, which is again a perturbation of the boundary data near of the boundary. Using this, you can work with derivatives, making some rich calculus, you are able to obtain the C1 estimates. In order to produce in global estimates, you just use this function key, which relates the gradient and the height of the function. And you work at a point where this function attains a maximum, and make derivatives of the equation around this point. You produce a third order equation, and you make some commutations using the curvature tensor, but at the end you produce a kind of maximum principle for the gradient for these equations. So this it's a rough summary of the technique, just to illustrate the method. And using these estimates, you have the existence result. Just for finishing, I present another results concerning closed graph this time. You have no Dirichlet problem, but some closed graphs. You consider some compact M, and you consider the manifold M bar is some interval times m, warped by some function h. And given some annulus here, you have two copies of m, say mt minus, mt plus. Consider this annulus. The problem is to show the existence of a graph inside this region which has prescribed mean curvature. This occurs if the mean curvature, the prescribed mean curvature, satisfies these three hypotheses. The first two ones are about the fact that these two copies of m works as barriers. So in order to have trivial barriers, you require these two hypotheses on h at the leaf, the upper leaf and the lower leaf. And the third hypothesis again measures the rate of growing of the prescribed mean curvature. Using these three hypotheses, you produce a closed graph with prescribed mean curvature. You may say that this same kind of result may be also applied for other closed problems. For example, for scalar curvature and the higher order symmetric functions of the curvatures, not only for mean curvatures. And the general result for this kind of problem was present in this paper. This time you may not use the continuity method, but a kind of degree theory developed by Yang and Li. And turning back to my work with Marcos, you point out some work in progress concerning this time anisotropic mean curvature. The problem is does not involve the area, but if you consider some hypersurface in M bar, you think about critical points. Say that the dimension is x, and this dimension is oriented by some unit normal vector field. And this time you consider this general functional. This is Lagrangian, elliptic Lagrangian, because f is assumed to be convex with respect to this entry. And if you think about balancing volume condition, you sum here some generalized notion of volume, where Q is some vector field, some ambient vector field. And if you extremize this functional with respect to emissions, he'll produce another version of mean curvature, because this time you have a distinguished vector field along sigma. This is the so-called anisotropic vector field, and the divergence of this vector key along sigma is constant, and this constant is this anisotropic mean curvature. This is a versional interpretation of this function, but you have also a tensorial interpretation of this, because you have some kind of Weingarten map, and HF is the trace of this Weingarten map. So all the problems you consider about the classical functional area may be restated in terms of this general elliptic functional. And then you may put the problem of, again, consider the non-parametric version of this, and to establish an existence result for graphs with prescribed anisotropic mean curvature. This is work in progress, and you'll see that the techniques you used before may be adapted, not so slightly, but with some nice adaptations. You may deal with this general problem in the next steps of the work. Well, I finished here, and parabéns to Marcos. Thanks.
Okay, does anybody have questions? I have one. Do you consider also the case that the flow lines of the conformal Killing vector field are closed?
Yeah, in this case, you may pass to the universal cover. If you are circles, you work in the universal cover of this.
What about singularities, zeros?
You drop the singularities because you are considering integrable distributions. For example, in the case of the sphere, if you consider rotations, you drop the poles.
Okay.
You are in the set of no singular points of the field.
Thank you. Any more questions? Okay, then let's thank the speaker.